Hello everyone, my name is Feng Zhang. I'm going to present our recent work on enabling efficient compressed data directly processing for various databases. This is a joint work of Renmin University of China, Tsinghua University, and Tencent. This is the outline of our presentation. First, let's look at our motivation. The first motivation is that the four V's of big data environment has four basic characteristics: volume, variety, velocity, and veracity. Due to the big data characteristics, the current database systems become rather diverse. For example, traditional database systems include TD Circle, MySQL, TiDB, HBase, SQL Server, Redis, and so on. Then, we have NoSQL database systems, including Amazon DynamoDB, CouchDB, and MongoDB. We also have graph database systems, including Neo4j and so on. In distributed and cloud environments, we have MPP database systems and cloud database systems. For example, we have MPP database systems such as Greenplum, and we have cloud database systems such as Amazon Aurora and Snowflake. Facing these various databases, how to address the big data problem becomes a challenge. Compression-based direct processing via rule-based compression is a computing paradigm we proposed in VLDB 2018, which can be explained from three levels: elements, rules, and DAG. Element is the smallest indivisible minimum processing unit. For example, in Figure A, each symbol represents a minimal data unit. Rule is a string of elements. We use a rule to represent repeated content, and a rule consists of subrules and data units. For example, in Figure B, Ri represents a rule. DAG is a rule-compressed representation. The relations between different rules can be organized as a DAG, as shown in Figure C. We can give each symbol and rule a number for numerical representation, as shown in Figure D. Then, the original data are represented as a sequence of numbers, as shown in Figure E. Based on the rule representation, we can perform common data analytics directly on the rule-compressed data. In this paper, we are trying to apply such rule-based compression to big data systems. We develop a new storage engine called CompressDB, which can perform data processing for databases without decompression. Since large data are usually stored in disk, our idea is to develop random update over compressed data in storage layer based on rule compression. In detail, as shown in the right figure, in an operating system, the lower layer is a storage system, such as Fuse and MooseFS. Based on these storage systems, we build databases such as SQLite, ClickHouse, LevelDB, and MongoDB, and these database systems can provide service to upper-level applications. Therefore, if we can integrate CompressDB to storage layer, then it can support diverse systems. However, in developing our idea, we meet the following three challenges. The first challenge is in element level. Complexities exist in using large element granularity. Previous Hadoop processes data at word granularity, while the storage systems usually organize data at a much larger block granularity. such as 1 KB or 4 KB. Simply increasing the processing granularity can reduce the compression effect, because two large data blocks can have part of the same data. The second challenge is in rule level. We need to operate rules for random update. Random updates involve great difficulties to handle, especially dealing with large amount of rules. In detail, random update on hierarchically compressed data needs recursive rule split, which is extremely inefficient when the DAG is deep. The third challenge is in DAG level, which is performance maintenance of real-time operation on the DAG in storage layer. When we develop random updates over compressed data in storage layer on the fly, the operations also need to be implemented in the storage layer for efficiency, because the access speed of the disk is much lower than the memory speed. We need to guarantee that the amount of data taken from disk by random access is as small as possible. Despite these challenges, we still decide to develop CompressDB in the storage layer, because storage space is much larger than memory size. Accordingly, an element in CompressDB represents a data unit like a data block. A rule represents repeated content consisting of elements and subrules, and a DAG is the organization of rules as discussed in previous slides. As for our novelties in element level, we introduce the concept of data hosts to allow updates in large data blocks. In rule level, we develop hashing and counting data structures for efficiently locating rules. In DAG level, we limit the depth of the DAG to retain the cost of rule split and merge within a small range. Such a design is of great benefit to database applications and can solve the challenges mentioned in previous slides. Database systems built on our storage engine can enjoy the time and space benefits of compressed data direct processing. We show the overview of our storage engine, CompressDB, in this slide, which can support various database systems. CompressDB consists of three major modules: data structure module, compression module, and operation module. These three modules support the database systems built on our storage engine. The first data structure module provides necessary data structures to both the compression module and the operation module. The second compression module supports hierarchically compression in file systems and can be applied to various block-based file systems. The third operation module can push down user operations to file systems. Next, we show our system design. The data structure module provides necessary data structures to both the compression module and the operation module. For example, the block hash table data structure provides a mapping from the hash value of a block to its block number. The block reference count data structure records the number of times a block is referenced in the file system. The block hole data structure provides the necessary information in update operations when block hole is generated. For the compression module, our general design is that when data are input into CompressDB for the first time, we use our rule-based method to compress the file to the system. In detail, we regard each block as a node. The indirect nodes represent rules, while the data nodes represent leaves. For the operation module, we develop operations including extract, replace, insert, delete, search, count, and they can be pushed down to the storage layer. The operation pushdown refers to that the data processing happens directly in the file system layer, which is a lower software layer. It allows direct processing techniques to occur closer to data, with which CompressDB can significantly reduce the amount of data accesses to disk and accelerate all upper-level database applications. In our implementation, we develop CompressDB in real storage systems, including Fuse and MooseFS, along with a set of operations. Databases can seamlessly use our processing on compression technology. In detail, we mount a file system in a directory, and then the system calls on this directory are handled by CompressDB. If the database system is set to store data in this directory, it can automatically enjoy the benefits of direct processing on compressed data, because CompressDB can handle the system calls like read and write. We validate the efficacy of CompressDB by supporting various kinds of database systems, including SQLite, LevelDB, MongoDB, and ClickHouse. We evaluate our method using 6 real-world datasets with various lengths, structures, and content in both single-node and cluster environments. We evaluate the performance of CompressDB upon the 4 popular and diversified databases. We evaluate the performance of these systems with and without our storage engine from the throughput and latency perspectives. On average, the databases using CompressDB achieve 14% throughput improvement and 44% latency reduction over the baseline. We show the throughput and latency for different datasets in this slide. Generally, the operations of CompressDB achieve much higher throughput over the original file system. CompressDB achieves 34 times throughput speedup over the baseline. We measure the space savings with a metric of compression ratio, which is defined as the size of the original data divided by the size of the compressed data. CompressDB achieves 1.81 compression ratio. We also conduct detailed analysis. For example, in the left figure, we explore the block size influence on compression ratio. We can see that smaller block size can increase the compression ratio. The right figure exhibits the trade-off between space cost and performance exchange, which shows that we can trade performance for space and vice versa. We use FileBench to evaluate the CompressDB in single-node and distributed systems. FileBench allocates a file set with various directories and files to simulate real workload, and then performs read and write operations to measure the I/O behaviors of given file systems. FileBench can output the results of throughput, latency, and bandwidth utilization. CompressDB achieves better performance in all aspects, including throughput, latency, and bandwidth utilization. We develop a novel storage engine called CompressDB for enabling random updates directly on compressed data. CompressDB can push down the operations to the storage layer. Specifically, we integrate CompressDB to file systems, which can support various database systems. Thank you. Any questions?